The key to understanding the action potential lies with two elements, sodium and potassium. Sodium is abbreviated as Na, potassium has just K. These are chemicals that are found in our foods and pretty much everywhere. They are both positively charged ions. Oh, and for the record, if you ever come into some potassium or sodium in raw form, don't throw it into water.
Catches on fire, and then it explodes.
To understand what this has to do with neurons, we have to zoom in to the membrane, the outer membrane of the neuron. And when we do that, we see that there's actually a lot of sodium and potassium as single ions floating around inside and outside of the cell. Remember, these ions, sodium and potassium, are both positively charged. You'll see in the membrane that there are a lot of proteins that span across the membrane. We'll talk about each of these and why they're important, but let's take a look at this protein first. This protein has a very specific job. What it does is it collects 3 sodium from inside the cell and then moves them outside the cell. Then it collects 2 potassium from outside the cell and moves them inside the cell. This is a movement of ions across the membrane, and it takes energy. Right? Where does this energy come from? Well, ultimately it comes from the food we eat, which gets converted into something called ATP, which is basically the fuel of the body. By expending ATP, this pump can move sodium outside the cell and potassium inside the cell. The key here is that 3 sodium are moved outside the cell and only 2 potassium are moved inside the cell. So what should we call this pump that moves sodium outside the cell and potassium inside the cell? Well, again, as scientists, we're all about creative names, and it's usually referred to as the sodium-potassium pump. So let's talk about the consequences of the sodium-potassium pump. All right? So we're looking at here, my little makeshift animation, is we're looking at the cell membrane here by these black lines, and the space here is going to represent what's going on with the sodium-potassium pump. We then have the extracellular or outside the cell fluid and inside the cell, and we have our potassium and sodium ions, which is what we're interested in. Remember, there's tons of things inside and outside the cell, but let's focus on these. All right, so right now, how many ions are there outside the cell? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What about inside? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 positive charges outside and 11 positive charges inside. Remember, both sodium and potassium are positively charged. We are at equilibrium as far as these charges are concerned. But when we turn on the sodium-potassium pump, what's going to happen, right? Well, remember, we are going to take 3 sodium and we are going to move them outside the cell. Then we're going to take 2 potassium and we're going to move them inside the cell. Right? Remember, all we're doing is moving positive charges, but what's happened to the differences in charges? How many positive charges are there outside the cell now? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, what about inside? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've reduced the charges inside the cell relative to outside the cell and created a net negative charge inside the cell compared to a net positive charge outside the cell. If we do this again, we take 3 sodium and move them outside the cell, and then we bring 2 potassium in, right? Now what are we going to have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, all right? Outside the cell and inside 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So every time we do this, we're building up a bigger and bigger electrical chemical gradient, right? But are we doing something else? Think of the sources of potential energy that we talked about. Is it just the electrical charge difference? No. Think about the first source of potential energy we talked about, the concentration gradient. What's happening to the concentration of sodium outside the cell compared to inside? Well, we're getting an area of high concentration of sodium outside the cell, an area of low concentration inside the cell. whereas we're building up a high concentration of potassium inside the cell and lowering the concentration outside the cell. By expending energy through ATP, that's the kinetic energy, we are slowly building potential energy in the neuron. Right? And we have two sources of potential energy: the electrical chemical difference, the difference in charge, as well as the difference in concentration. So that's where the potential energy comes from. But how is it released in order to send that signal down the axon? Well, in order to do that, we have to understand the other proteins that we see spanning the membrane. We have two more proteins here to talk about: the sodium voltage-gated channel and the potassium voltage-gated channel. These proteins are what make the action potential, that electrical signal down the axon, possible. So what we're looking at here is a graph of the change in electrical potential from inside the cell compared to outside the cell. This is an action potential, the release of that potential energy in order to create that electrical signal. We start at a resting potential. Roughly negative 55 millivolts is the resting potential of inside the cell compared to outside the cell. Why is it negative? Well, remember the sodium-potassium pump, right? It's slowly producing a net negative charge inside the cell compared to outside the cell. As information comes in the dendrites, that begins to move towards the positive direction, bit by bit. When it reaches a threshold, suddenly the sodium gates are going to open. This is why they're called voltage-gated. At a particular voltage, the gates spring open. Now there is a giant hole that's going to allow sodium through it. So, what's going to happen? Well, remember, we have two sources of potential energy: concentration and electrical potential. So once we open up a gate, all of the sodium ions are going to move from outside the cell to inside the cell to equalize both the concentration and the charge. This is going to create an influx of positive charged ions moving inside the cell from outside the cell, creating a much larger positive charge compared to the inside of the cell versus the outside of the cell. This is known as depolarization, and we can see it on the action potential graph. At a certain voltage, the sodium gates are going to slam shut. Again, voltage regulated, and now the potassium gates are going to swing open. Well, now what's going to happen? Well, now we have a difference in charge between inside and outside the cell, and a difference in concentration of the potassium inside versus outside the cell. So the potassium is going to flow from inside to outside. And this is what we call repolarization, because as the positive charge of the potassium flows from inside the cell to outside, we're now going to move back in the negative direction. Except now we have a problem. We have all of the sodium inside the cell and all this potassium outside the cell. This neuron can't fire again, right? It's now equalized. It can't fire. We need to somehow move the sodium inside the cell to outside the cell and get the potassium outside the cell to inside the cell. If only we had something that could move sodium from inside the cell to outside the cell and potassium from outside the cell to inside the cell. Huh. Oh yeah, we got that sodium-potassium pump. With the voltage-gated potassium and sodium channels now closed, the pump is still working, and slowly over time, it's going to reset the neuron, allowing it to fire again. Right? So during this time period, we have this refractory period where the neuron can't actually fire again until the sodium-potassium pump resets up those concentration and electrical gradients. One thing that's very important is that the action potential is not like electricity down a wire. It's not a flow, right? Because the movement of charge is occurring at the specific proteins. So it's more of a discontinuous function where the charge changes at each protein, so it's kind of leaping through it, right? It's not a nice continuous function. This is actually a really slow way to move a charge. It's similar to what you might imagine with dominoes. In dominoes, right, it's not a continuous string. Each domino is a separate individual point. As we tip it over, the next domino tips and the next domino tips, and on down it goes, making a really fun game. But this can be a really slow process, right? And if our neurons need to move quickly, we need a way of speeding up the effect. Take a look how these dominoes are set up. The ones on the left are connected the way you would normally set up dominoes, while the ones on the right have large gaps, but they're connected via a straw. What do you think is going to happen when they tip over the first domino for each row? What is the difference going to be? So pause for a second, come up with your answer, and then let's take a look. You can see that those dominoes connected via the straws are much quicker at transmitting information. Right? By having that instantaneous physical gap present, we can dramatically speed up the flow at which the dominoes fall. Turns out our nervous system has evolved just such a system. It's known as the myelin sheath. Most of the axons in our nervous system are myelinated. They are surrounded by a tissue of highly insulatory fat that prevents the electrical charges from moving. And there are little tiny gaps between the myelin sheath, called nodes of Ranvier, that allow for the transfer of information. That means that the electrical signal actually leaps between those nodes, much like the dominoes leapt between the gaps using the straws. This dramatically increases the strength of the signal and dramatically increases the speed of the signal.